All right, let's take a look at the homework from last night. Page 201, you did numbers 9, 10, and 12, graphing some parametric equations. And parameter, remember, we call them parametric equations. Our root is the parameter, right? What is a parameter, Quentin?
It's like the shape of something.
Jamie?
The boundary.
Okay, it's a boundary, it's a limitation. So with parametric equations, the parameter would be
The T.
an extra letter. It's a third letter. So we know x and y get graphed, but when you introduce a third letter that has limits placed upon it, that therefore also limits the x and y, that's where we get our parametric equation. So the parameter, remember, is the name for that extra variable. Number 9 on the homework, you were given the extra variable was t. And a lot of times it is, not always. We were given the equation x is equal to t plus 1. We were also given that y is equal to t squared. And we were told that t is between -2 and +2. So if we wanted to graph the parametric equation, I said the first thing you'll want to do, back to Quentin, is
Set up your TXY table.
set up a TXY table, or whatever the letter happens to be. In this case, it's t. And start by writing all the easy values for the parameter.
-2, -1, 0, 1, 2.
There we go. And for the x, we're simply going to take that t, that parameter, and add 1 to it. Jamie?
-1, 0, 1, 2, 3.
All right. And then for the y value, we're simply going to take the t value and square it, Quentin.
4, 1, 0, 1, 4.
But when we graph, we're only going to actually graph class
X and Y.
x and y. The t only was there to limit the graph. We're done with it now. We're just going to plot these 5 points and connect those points. And let's see what we should have gotten here for our graph. And I'll do a kind of a quick sketch here. Don't need a whole lot of room because the numbers aren't particularly large. I like that. So we've got -1, 4. Should have had a point there. 0, 1, 1, 0, 2, 1, and 3, 4. And we can see here that when we only draw these points, we get not a full parabola, but the end of the parabola here. And we have a graph that looks something like that. All right, taking a look at the next one. For number 10, we were given that the x, in fact, let me do yellow here. We were given that the x is equal to a t squared plus 1. We were given that y is equal to 2t. And then we were told that once again, t is between -2 and +2. So once again, Jamie, as we set up our
TXY table.
we're going to plug in the easy values for t.
-2, -1, 0, 1, 2.
And for the x this time, we're going to square and then add 1. So if we square and add 1, Quentin, we get
5,
then,
2,
then,
1,
then,
2,
then.
5.
And for the y, we're going to double all of our t values, Jamie.
-4, -2, 0, 2, 4.
And I think this will fit just fine on this graph grid as well. You should have plotted one at 5, -4, 2, -2, 1, 0, 2, 2, and 5, +4. And when you connect these, now our parabola is a little wider. And it's turned sideways. So a little bit more of a rounded shape there. But again, not a full parabola, only that limited piece, limited by the parameter. How do we do on the next one?
See what I did wrong. I accidentally had an x squared for that first equation, so my answer is like square root of 5 square root.
Oh, okay, you just copied it wrong.
Mm-hmm.
Okay, all right. Any questions, comments on this one? All right, then the last one we had was fun. We were given for number 12 in the homework. Our parameter wasn't t. Our parameter here is on number 12? That's not theta. The other one. Testing your memory here. Phi, there we go, phi. All right, so we've got a phi x, y table. And go ahead and just have plenty of room here. And my suggestion is if you're going to use angles, and they have phi here limited, I say limited, I mean it's not very limited, right? 0 to 360 isn't much of a limit, but limited from 0 to 360, where x is equal to 3 times the cosine of phi, and y is equal to 4 times the sine of phi. And I said a good value to use for phi might be every 30 degrees might be a good idea. So we'll go 0, 30, 60, 90, 120, 150. I'm thinking the virtues of 45-degree increments. 180, 210 degrees. Maybe the next one will do 45s. 240 degrees, 270 degrees, 300 degrees, running out of room. 330 degrees, just going to make it 360 degrees. And I'll slide the camera over in just a second and make sure we get the whole thing on there. Okay, so what you had to do is take cosine and then triplet, cosine, triplet, cosine, triplet, cosine, triplet. But remember we said we're going to get a lot of patterns. We even see patterns here, right? Negative 1, 0, 1, 2, 3, right? 4, 1, 0, 1, 4. 5, 2, 1, 2, 5. Negative 4, 2, 0, 2, 4, right? There's patterns in all of this, but especially when you involve angles into the mix. So we're not actually going to calculate all of these. But we're going to start by taking 3 times the cosine of 0, class.
Wait, no, I have
3. 3 times the cosine of 30. 3 times the cosine of 30. Oh, not 30 times 3, then cosine. Take the cosine of the 30, then multiply the cosine times 3. Otherwise, you would have gotten 0.
Oh, I was reading my mind, sorry. Yeah. 2.6.
2.6, and that's what you had said a moment ago. All right, for 60 degrees.
1.5.
For 90 degrees.
0.
120.
Negative 1.5.
Stop. What's the next value going to have to be?
Negative 2.6.
And then,
Negative 3.
think about this. This is the cosine. Positive in the first quadrant. Negative in the second quadrant. Negative in the third. So I'm going to expect the mirror to happen here. I'm betting negative 2.6. Is that correct? And so then,
negative 1.5.
and then 0. And then here it should go back into the positives, right? So I'm going to expect 1.5. And there we go. Right, so we don't actually have to calculate anything more than, I guess we did the first 5. And the rest of it, we just, maybe fact check 1 or 2 along the way would be a good idea. The lines are all different lengths, so this one's just noticeably shorter. Right? I'm not OCD or anything. Maybe slightly. All right, so now let's do it with the 4. All right, so sine this time, and then times 4 gives us 0.
2, 3.5, 4, 3.5, 2.
I'm going to guess negative 2?
Yes.
So negative 3.5, negative 4, negative 3.5, negative 2, and 0. And that was all off of the first 5, right? So although it's a lot of writing, I suppose, setting up that chart, which is, I'll grant you, it's annoying because I'm lazy, but it really isn't hard math once you get through the first few, once you see the pattern. So let's give myself some room here now. Kind of like the last graph we did in our last lesson that involved sine and cosine. My biggest number is a 4, right? Biggest absolute value is a 4. So I don't need a graph that goes to, 9 or 10. So maybe I'll do every 2 boxes as 1. And see if that maybe makes these decimals easier to graph. Because normally decimals are a pain, right? But if I made every box 2, then every 2 boxes 1, then each box gets to be a half. I could probably get a pretty accurate graph off of that. Did either of you think to do that?
I did what we did the other day with 4 boxes.
You did 4 boxes. So you actually went 16 boxes out to 4?
Up and down, but not.
Wow. Okay. So you did every 4 boxes still 1. Now that makes it really accurate, just makes it really big. I'm a little more lazy than that. Did you do just every box 1? All right.
I can see it.
I'm going to call this 1, 2, 3, 4. 1, 2, 3, 4. Negative 1, negative 2, negative 3, negative 4. And negative 1, negative 2, negative 3, and negative 4. Zoom in just a little bit more for the graph's sake. All right. So my first point, class, is
3, 0.
3, 0. Then
2.62.
2.6 is going to be just past my 2.5 and then up to 2. All right?
1.5,
1.5, 3.5 is spot on.
0.4.
And then notice the next point is going to be negative 1.5, 3.5. You see the symmetry? So then my next one's probably going to be negative 2.62. And then negative 3, 0. And I'm going to guess we're going to keep coming down here to the third quadrant now and go negative 2.6, negative 2. And now I'm just cheating. And just making it match up. And of course we see we're going to get another ellipse. And so kind of come down this way is a nice smooth curve. Nice smooth curve. Oop. Shotgun pushed up in the holder. And nice smooth curve, sort of. And there we go. And it looks pretty decent. All right, and both of yours look pretty good as well. Though I will say the bigger it is, the harder it is to keep that curve going. His curve actually looks nicer because he didn't have to keep it going as long as you did. So I kind of hit the balance between yours and his. I always gave myself easier accuracy than he had, but not as big a graph as you had to have. All right, questions on this? All right, let's do another fun one, but you're going to have to switch your calculator to Radian mode. We're going to go Radian mode here as we take a look at number 21. Number 21. And let's see, here on 21, we've got x is equal to r cosine theta plus theta sine theta. Almost seems like complex trig form, but it's not an I sine theta, it's a theta sine theta. And then y is equal to r sine theta minus theta cosine theta. Now, why do we have to use radians? If all you're doing is taking the sine or cosine of theta, you can use degrees. But if theta is a standalone variable without a trig function like you see here, that tells you have to use radian mode. Now, they bless us here on number 21 because they tell us our r value is going to be 1. And if r is 1, you distribute a 1, it's as if it doesn't even matter. Does that make sense? All right. So we're switched to radian mode. I don't need to worry about the r. I'm just going to go theta x y. And I said I don't want to do the whole 30-degree thing again, okay? Because that's a lot of points. So let's do 45s. But we can't do 45 because we're not in degrees. We're in radians. So we'll still start at 0. And they said that we're using 0 to 2 pi, right? So theta here is between 0 and 2 pi. We're going to start at 0, but 45 degrees later is what radian measure? Pi over 4. And then the next 45 would be 90, but that's pi over 2. Then the next 45 degrees is an additional pi over 4. So we have 1/4, 1/2, 3/4 of a pi, right? So 3 pi over 4. And then another quarter pi would be pi. Add another quarter pi. 5 pi over 4. Add another quarter pi. 6 pi over 4, but we can reduce it. 3 pi over 2. Then another quarter pi. 7 pi over 4, and then finally 2 pi. This gives me enough points I should get a pretty decent curve, but not so many that I'm driving myself absolutely crazy. Though, admittedly, this is going to be a bit of a pain. All right, so here we go. Start with 0. Now, I know when I plug in a 0 here, this whole thing's just going to drop out. So really, because 0 times anything is 0. So I really just need the cosine of 0. 1. And for the sine, for the y value, it's going to be the same thing, right? This whole thing is going to drop out. So it's really just the sine of 0. That's the one easy one. Now the fun begins. All right, we're going to take the sine of pi over 4. So pi over 4 sine times pi divided by 4. Plus, parentheses, pi divided by 4, close parentheses, cosine equals.
1.26.
Did you get 1.26 also? All right, so we'll round it off to 1.3. We're kind of working our way backwards. Now, if you have a direct entry calculator, you can literally use sine, parenthesis, pi over 4, close parenthesis, minus, parenthesis, pi over 4, close parenthesis, cosine, parenthesis, pi over 4, close parenthesis, equals. We're doing it in reverse. We're going to start with the cosine pi over 4. So pi divided by 4 equals cosine times, parentheses, pi divided by 4, close parentheses. Now put a negative on whatever you've got, or equals, and put a negative in front of that. Plus, parentheses, pi divided by 4, close parentheses, sine equals. 0.15, blah, blah, blah. Or maybe round up to 0.2. All right, so here's what we're going to do now. Quentin, you get pi over 2, x, and then Jamie, I'm going to have you do the y for pi over 2. So we're going to divide and conquer here, okay, to save some time. So Quentin, find the x using pi over 2. Jamie, find the y using pi over 2. If you're at home, if you want to pause the video and give yourself time to calculate both, you can, or just pick one, and we'll roll with that one.
I can't promise that I'm going to be doing it right. I can't promise I'm going to be doing it
Well,
right.
I do have the answers written down, because I did these already, so I've got a way to fact check you. Quinn's got his?
Negative 0.62.
That is not what I got. For x? All right, so we're going to start with the pi over 2. Oh, you hit the equals too soon. Okay, so let me walk you through the x one more time. So you're going to start with, in fact, you know what you could do? You could do the pi over 2 in the memory. That might be quicker because you're going to use it 3 times anyway. Let's try that. Let's try pi over 2, which is the 1.57 blah, blah, blah. Store it in the memory and do sine recall 1, or recall 1 sine times recall 1 plus recall 1 cosine equals.
1.57.
That's what I got, 1.57 or 1.6. All right, Jamie, you could do the same thing if you put in the memory. You do recall 1 cosine times recall 1 equals, put a negative in front of it, plus recall 1 sine equals.
I have negative 1.5.
That is
The
also
first time I got it 0.7.
That's also not correct. Okay, so we've got it in the memory, right?
Let me make sure it's the right thing.
Yes, okay. So recall 1 cosine
Cosine.
times
I'm degree mode again. Okay, let me see.
the recall 1 cosine times recall 1 equals, make it a negative, plus recall 1 sine equals. There we go. And it becomes evenly to 1. And that happens because the cosine of pi over 2 is 0. So that whole thing ends up becoming a 0. All right, now do the same thing with 3 pi over 4. Put it in the memory, and we'll divide and conquer again. So figure the 3.4, put in the memory. No, you're not going to have one quite like this on a quiz or test.
I was
But
about to
we're
say.
just doing this for the fun of it, okay? And Quinn's like, yeah, fun, right? That was quicker with the memory, wasn't it? What do you got?
0.958.
Good, 0.95 rounds to 1, okay? But not exactly 1, it rounds to 1, all right? And then Jamie,
A negative 2.3.
I don't have a negative, I have a positive 2.3.
I imagine the negative little like things when they shouldn't have, I guess.
Yeah, should have just done it here. Let me watch it you again. You still got it in the memory, right? So recall 1. And we'll take the cosine.
And then I multiply.
Recall 1 equals plus recall 1 sine equals. All right, do that one more time. So, okay, so let me see the memory. Okay, so we take the cosine times recall 1 negative plus recall 1 sine equals. I got a negative 2.3. I had a 2.3, I just didn't have a negative 2.3. Oh, you're in degree mode.
That isn't happening.
Yeah. Radian mode. That's why. Okay, try that again. I was not wrong. I was about to say, man, how was I wrong? Okay.
Okay, now it's falling.
Okay, and you know how I knew it couldn't be, Jamie? Because I realized this is a quadrant 2 angle. It has to be negative. So this negative has to make it positive. And this has to be more positive. So there's no way it could be negative. And thinking those thoughts made me fact check you and be like, unless she's in degree mode, that's what it was. Okay, so we do have a positive 2.3. All right, now make sure you're in radian mode. This time you don't need a memory because you're just going to hit pi instead of recall 1. Really easy, and you apparently already did it. Show off. What do you got?
-1.
Comes evenly to -1. All right. Jamie's about to put her pi in here.
I have 3.14.
Good, comes evenly to 3.14. We'll say 3.1. All right, now we're going to switch. Jamie, you do the x. Quentin, you do the y for 5 pi over 4. And have you noticed there's no pattern yet? If there were, we'd be stopping and we'd just go from here. But there's not a pattern yet. Quentin's on the bottom with the y, you're on the top with the x. We're doing 5 pi over 4, putting it in the memory. Whoa, stop over there.
I have 1.26.
That is not what I got.
2.06.
I did get 2.06, so we're rounded 2.1 for the y. All right, Jamie, let's do the 5 pi over 4. And you're in degree mode somehow. How do you keep doing that?
Because I need to clear and like it's all messed up and then.
So every time you clear, no, you shouldn't go back to degree mode.
I'm used to. Sometimes when I do that, like it won't work, so I like turn off and then on, and that's why.
Oh, okay. When you turn it off, that's strange. Yours defaults back to degree mode. Yeah. So make sure it's in radian mode. Let's do the 5 pi over 4. What have you got now? Negative
3.48.
That's what I have. Negative 3.48. So negative 3.5?
Mm-hmm.
All right. I apparently did not round. I have negative 3.4. All right, do the 3 pi over 2 now. Make sure you're in degree mode. Or radian mode. 3 pi over 2. Quentin's finding the y. Jamie's finding the x. Quentin already found the y.
-1.
Go on to the next one, Quentin. And Jamie's like, nah. Victoria on YouTube, you pause, wait. I'm kidding. I'm sure you're already like, you're done with the whole chart. You're just waiting on us. Fast forward. They're still not done.
I have negative 4.7.
Hey, look at that. Negative 4.7. All right, there we go. All right, you got the next one yet?
Mm-hmm.
What do you got?
Negative 4.6.
Negative 4.6. Yeah, I'm still not seeing any patterns. All right, go and do both of the 2 pi's, Quentin, while Jamie does the 7 pi over 4 for the x.
Negative 3.18.
Negative 3.1. And Quentin has some of the answers here.
Yes, x is 1.
And we'll find the y, whoever gets it done first.
I always saw that.
Oh, he already did it.
Negative 6.3.
Negative-
Or 6.3.
Negative 6 point who?
3.
Ooh, that's not what I have. I have negative 6.8.
Negative 6.283.
Fact check that. Do the 2 pi and the y. 2 pi cosine times 2 times pi, make it a negative, plus 2 pi sine equals.
I have negative 6.136.
Tell you what, try putting 2 pi in the memory. Let's see
That's
if we
what I
can.
did.
You did do the 2 pi in the memory. Okay, let me see the. Oh, you're in degree mode, radian mode. Don't cry, Jamie. Don't cry. Make it a negative plus recall 1 sine. Still negative 6.28. Random string. All right, negative 6.3. Okay. All right, I'm going to trust that you're right. Even though my numbers say otherwise. All right. So notice no pattern on this one, which is just obnoxious. Well, here we go. Let's plot these here. Maybe use the same graph grid you did earlier. If you have a new graph grid already set up, we're going to go. Again, we're not graphing this part, so it's going to be 1, 0 for our first point. Then we've got, this is going to be fun, 1.3.2. And this is where it's helpful if you at least have 2 boxes to every one. Then we've got a 1.61, 2.3, negative 1, 3.1, negative 3.5, 2.1, negative 4.7, negative 1, 3.1, negative 4.6, and I'm running out of room for my next one. My next one would be 1, and then like negative 6.3, be something like that. And we've got to be able to connect this all with a nice smooth-ish curve. I did kind of straight line here at the end, didn't I? And kind of picture a spool of thread here. Remember we talked about that shape where if you unwound the spool, that's what this one here is, that involute of a circle. So imagine a radius 1 spool spinning out. And that's what you would get. All right, questions on that one? And you can tell, look, there's no symmetry in the graph either, is there? So no wonder there was no symmetry about the points that we were trying to plot, which is, just obnoxious. All right, let's go to a less obnoxious one, I think. That's number 25. Number 25. Now notice, theta is not used as a constant here. The only way theta is used is in the trig function. So we don't have to use radians, which is really happy. All right, so we can go back to degree mode and stay there for this problem. I still might do 45s though, instead of 30s. We have x is equal to cosine cubed theta, and y is equal to sine cubed theta. And let's do 45 degree angles here. So 0 degrees, 45, 90, 135, 180, 225, 270, 300, 315, and 360. Zoom in a little bit more here. All right, so what we're going to have to do here, obviously, is when we find the cosine, we're going to have to cube it. Now on your calculator, I believe the cube button is second function of the 0. Is that correct? Second function of the 1. Okay. So what you're going to do is you're going to do 0 cosine, and then second function 1 to cube it. Do you get? 1. 45 cosine, second function 1. Point 0.35? All right, cosine 90, second function 1. Again, if you've got a different calculator, you would do cosine 45, close the parentheses. You might hit equals and then cube it, or at least close the parentheses, raise to the third power, maybe caret 3. So close the parentheses, caret 3, see if that's giving you the correct values here. 135. Okay, I'm seeing a pattern already. What do you think the next value is going to be? Negative 1. What do you think the next value is going to be?
Negative 3.5.
Negative 0.35?
Yes, sir.
And then 270 probably 0. 315, 0.35, and then a 360, a 1. All right, let's go to the y. We're going to do the same thing but with sine. So sine 0, or 0 sine, cube it. All right, 45 sine, cube it. 90 sine, cube it. 135 sine, cube it. Okay, so what do you think the next number is going to be? 0, then what? Right, because we're first and second quadrants positive, we should delve into the negative, so probably negative 0.35, negative 1, negative 0.35, 0. Well, let's see how this goes. Now notice this time, 1 is my biggest value. So I really could stand to give myself a stretched out unit here. I also don't need a particularly large graph, but if we do 4 boxes to 1, that should be ample. So 1, 1, negative 1, negative 1. So starting at 1, 0, then 0.35, 0.35 is going to be right about here, 0, 1. You kind of see it's got a little bit of a curvature here. Do you see that? It's not going to be a straight line. You know, it might not hurt. Let's do 30 real quick. Do 30 for the cosine real quick. I just want to get another number. Cosine 30, cube it.
0.64. Well, 0.65.
0.65. Okay, now do sine 30, cube it.
0.125.
0.125, so 0.13-ish. All right, so that would be 0.65, 0.13. So right about here. Let's do 60. Because of the pattern, I'm not going to have to do all the 30s and 60s, but let's at least do a 60 and see what that number is. Ah, that's the 0.13, and then the sine cubed ends up giving us a y value of
0.65.
Do you see how those are just trading places? Okay, so that means we're going to go 0.13, just about halfway here, and then up 0.65 is going to be right about here. Okay, 0.13 has to be here. 0.65 be right about there. What's that number? 0.35? Ah, 0.35 would actually be closer down here, more in this corner. because this is a half, this is 0.25, 0.35 is closer there and here. All right, so we get, actually it is a little more pronounced than I originally had. And we get that curve there. Now watch what's going to happen as we go into the second quadrant. If we just plotted the negative 0.35, 0.35, and the negative 1, 0, see how it's these same points again? So it's also going to mirror here, and it's going to mirror here. And so we've gone up, now we're going to go down. Do you see the same thing's going to happen in the third quadrant? Negative 0.35, negative 0.35. And the 0, negative 1. And then again in the fourth quadrant, positive 0.35, negative 0.35. And we get that shape there. And this is what's called a hypocycloid. All right, now I don't know a football fan. Maybe you recognize this. There's a football team that has 3 of these. One red, one yellow, then one blue, kind of in a triangle pattern. Pittsburgh Steelers.
No,
Pittsburgh Steelers have this, and this. So this symbol, 3 of them, is the symbol for steel that you might see sometimes. So anyway, that's a hypocycloid. But it's one of those, it's weird because it comes to a point, to a point, to a point, and to a point, all the way around. So kind of an interesting look there. I wanted to do number 23, which is a curate cycloid, but for sake of time, we will have to pass on number 23. Let's get to the next thing in your notes. Eliminating the parameter. Eliminating the parameter. Let's talk about parametric equations, again, kind of from the start. If we looked at this equation, x is equal to 2t, and y is equal to 4t negative t squared. And supposing I didn't put any limits on t. Suppose I either said that t is negative infinity to infinity, or I said nothing about t whatsoever. Does t serve a purpose? No. For instance, if your parents are like, all right, I know you got this youth activity you're planning to go to, I just want to talk about a few guidelines. You can do whatever you want. Now, I don't know any parent in their right mind who would say that to a kid. Okay, you can do whatever you want. Okay, that's not wise. But if they did say that, okay, stretch it. Was there any point even having that talk? Would you say that there were parameters they gave you? No. If there were no limitations, the parameter is useless or needless. If there is no parameter limitation, we might as well eliminate the parameter. Does that make sense? How do we eliminate the parameter? Step number 1, to eliminating the parameter. If it is useless, if there's no restriction on the parameter, we might as well eliminate it. Step number 1, solve the easier equation for the parameter. Solve the easier equation for the parameter. Which of these two equations, the x or y equation, appears to be easier? Certainly the x equation. We're going to solve it for the parameter. We're going to get t by itself and say that t is equal to x over 2. Step number 2, substitute for the parameter in the other equation. Substitute for the parameter in the other equation. Which means we're going to take the x over 2 and we're going to drop it in right here and right here. So that my y equation becomes y equals 4 times x over 2 minus x over 2 squared. And of course, if you square an x over 2 class, you get x squared over 4. If you multiply 4 times x over 2, you can either get 2x, or if you left it this way, 4x over 2. But I really hate fractions, you know? So I'm going to multiply everything by the LCD, which is 4. And if I multiply everything by 4, what does my equation become now?
4y equals 8x minus x squared.
And there's my equation. This is a parabola. This, if there were a limitation, in fact, this is one of the problems we did yesterday. This was a piece of a parabola yesterday because there was a limit. No limit, there's the whole parabola. Make sense? Eliminating the parameter is just replacing the parameter with its equivalent and going from there. Obviously, there's no parameter left. If we graphed it, it would be a parabola that goes to infinity, but not beyond. All right, write this one down. X equals t squared, and y equals t negative 2. Again, this is one of our parabolas we did yesterday, but we had a limit on the parameter. Here I have no limit on the parameter, so there's no point even having the parameter. So let's solve the bottom equation for t to say that t is equal to, and then we can substitute to get x is equal to y plus 2 squared, or if we were to expand it,
y squared plus 4y plus 1.
and there again we see another parabola, one squared, one not, right? But it's the whole parabola now. It's not just the piece that we've been limited to yesterday when we had a limit on our parameter. Does that make sense? Mm-hmm. So if there's a limit on the parameter, when you go to graph it, you abide by the limitations. If there is no limit, you might as well just get rid of it. At the top of page 201, there are no limits on any of these parameters. So on numbers 1, 3, and 5 at the top of page 201, I want you to eliminate the parameter in each problem. Eliminate the parameter in each problem. 1, 3, and 5 at the top of page 201. All right, let's take a look at these. What did you do on number 1, Jamie?
I got t equals x minus 2.
All right, so we just move the 2 over, isolate it, t is x minus 2, and then?
And then I put in the other equation and got y equals x minus 2 minus 1 and combine that to get negative 3.
And there we go, a linear equation, right? If we graph this with a parameter, we get a piece of the straight line. Since there is no parameter now, we get the entire straight line going to infinity. Do we have that?
I had x equals y plus 3.
And that would be the same thing, right? If you move the 3 over, x equals y plus 3 is the exact same equation. So yes, both of those are correct. Good question. All right, look at the next one, number 3. Here we actually have 2 parameters, and neither one's doing anything. So, Quentin?
T equals x, okay.
You could do that. Let's go with that. Let's say t is equal to x over k.
And for the answer, y equals square root of 1 minus k squared times x over k squared. And k squared is from cancel.
Well, good, because this becomes x squared over k squared. Or did you say that? Did you say x squared over k squared? Or did you say x over k squared?
Yeah, I said x over k squared.
X over k squared, which becomes, of course, 1 minus k squared times x squared over k squared. And then you said we're going to
Cancel the k squared.
get
Y equals positive negative square root of 1 minus x squared.
And if we wanted to get rid of the radical, we could square both sides to get what?
Y squared equals positive negative, or no, positive 1 minus x squared.
There we go. Or if we want to bring that over, we could say x squared plus y squared equals 1. That would be a circle. So we could do that as well. There is an easier approach, and it's to say that technically the parameter Katie has already been isolated. K squared t squared is the same thing as kt squared. So this is x squared. And then we square both sides. So we could have done it even that much easier, but nothing wrong with the approach that we used, right? Because there were both parameters there. Questions on that one? Looking at the last one here. Which t did you isolate, Jamie?
The t minus 3.
Okay, to get...
t equals y plus 3.
Okay, and then we had to...
Substitute that, and it was x square root of y plus 3.
But we really don't like radicals, so...
On my side.
The only thing with squaring both sides, though, what will happen is you'll create a full parabola where this is only half a parabola. So, you know, maybe it's best to leave it in this way, right here. Again, if you try to isolate this, you'd have to square both sides. But again, you're creating an extra part to a graph that should not have been there originally. This is the best way to solve it, and best to leave it in that way. Here, it wasn't a problem to square because you already had positive, negative. So you already have positive and negative. Squaring it doesn't do anything. Here, when it's just a positive, you square that, you just created a second side. So we'll probably leave that one just like that. All right, questions on these? All right, your homework for this evening is to eliminate the parameter on these three problems on page 201, numbers 2, 9, and 10. Now, I realize 9 and 10 supposedly have limits. We're going to imagine those limits don't exist, and we're just going to get rid of the parameter on numbers 9 and 10. And of course, on number 2, it does not give a limit, so we definitely would have to eliminate the parameter there. Don't forget, we have a test coming up in lesson 115, and that'll be over chapters 9 and 10. So we're just about wrapped up. In our next lesson, we'll kind of review over this, make sure we're good to go, and then we'll have a full review over chapters 9 and 10, and then test in lesson 115. All right, when the bell rings, you'll be dismissed.